And so some of the ones I was looking for, you know, would be like, what's this one? Borate, carbonate, nitrate, fluorate, chlorate, bromate, iodate, then silicate, phosphate. You could have gone more if you wanted to push for bonus. This would be called antimonide, but I didn't put up the periodic table until at the end. Tellurate, you could have seen it over there. Bismutate, this one's radioactive, so ignore that one. In addition to that, there are the ones that you just have to memorize, which were what? Giants. Chromate, dichromate, permanganate, and oxalate, and you know, I forgot one. I forgot one of the most common ones. I forgot to write it up on the board. You know what that one is? One of the most common eights. I believe we forgot to write. Forgot it this morning too. What's this? C2H3O2 acetate. I don't know why I forgot it. Yeah, keep working on those. But we don't have time to keep working. Lost the lap period, so you can turn in exercise A with the exam. We have to move on, and in order to save some time, I'm not going to go through all the PowerPoint slides for Chapter 7. But we will take a look at the objectives. Looking at the learning objectives, given the formula of a chemical compound or name, state the number of each element. In other words, can you write the formula? Or actually, this is nomenclature is the last one. This is just figuring out how many atoms. So for example, water. What's the formula for water? H2O. How many hydrogen atoms? How many oxygen atoms? Oh, so you've accomplished learning objectives 7.1. Check. 7.2. Distinguish among atomic mass, molecular mass, and formula mass. Calculate the formula or molecular mass of any compound whose formula is given. So we're going to talk about that. 7.3. Define the term mole. Identify the number of objects that corresponds to one mole. The mole is a counting unit. Yeah. It's like define the term dozen. What is a dozen? 12. Because we're going to define it in a little bit more. I mean, so the mole is just a counting unit like a dozen. However, we need to know where it came from, the origin of that number. Now, do you know the origin of 12? I mean, why 12? Does somebody know why 12? I mean, why isn't a dozen 10? You know? In fact, if you had 10 loaves of bread, what would you call it? 10 loaves of bread, but if you had a dozen donuts, it'd be 12 donuts, right? But why a dozen? Does anybody know? I don't know exactly either, but a mole we have to know. All right, 7.4, define molar mass. Okay, we're going to be talking about what molar mass means. 7.5, we're going to be doing calculations using all these definitions and concepts here. 7.6 talks about percent composition. You know, when we talk about percent composition, we can talk about it in terms of atom or mass, or dozens of atoms, or moles of atoms. We'll talk about that. Distinguish between an empirical formula and a molecular formula. We'll talk about that as well. All right. Given data from which the mass of each element in the sample of a compound can be determined, find the empirical formula of the compound. Okay, 7 and 7.8, this deals with something called chemical analysis. In chemical analysis, oftentimes we send out a sample. And when we send out a sample for analysis, what they give us is they don't give us the formula back. It'd be nice to know, we send out a sample, tell me what it is. No, it's H2O. No, if I sent this sample out for analysis, you know what they'd give me? Oh, that sample consists of 89% oxygen, 11% hydrogen, by mass. So they figure these things out. And then we would have to figure out, 89% oxygen, 11% hydrogen. What is that? By mass, that's H2O, that's water. Now that's because water, when we're talking about formulas, that's because there are different ways of representing the composition of water. So let's take a look at formulas first. When we look at a formula, it's an atom ratio. And this tells us the composition atom by atom. So when we look at water, we immediately recognize H2O. That's because it's atom, 2 atoms of hydrogen for every atom of oxygen. But if we did a mass ratio, it would look quite a bit different. There are different mass ratios we could do. But one of the mass ratios, let's figure out, let me tell you what it is. Mass ratio. It'd be hydrogen, 11.20 sub 9. We'll just do this to 4 sig figs. And oxygen would be 88.790. That would be the mass ratio. So for every 11.209 grams of hydrogen, we have 88.790 grams of oxygen. So mass ratio. But when you look at the mass ratio, do you immediately recognize that as being water? No. And so typically we don't use the mass ratio to represent the composition. However, we could use the percentages. So, for example, here you could do a percent by, we call this an atom percent, percent by atom. Or we could do dozens of atoms. We'll talk about that. Or we could do moles of atoms, which we'll get to eventually here. And so if we just do this by atom, then the percent hydrogen by atom would be, how many hydrogen atoms are there? There are 2 hydrogen atoms over a total of how many atoms? In this case, it would be a total of 3 atoms. And so it would be H would be what, 2/3 or 33%. H. We could go more digits here if you wanted. In fact, I could just write 33.3% H. And this is an atom percent. Atom percents are also known as dozen percents. So for example, if I had 2 dozen hydrogen atoms, how many total atoms would there be? At 2 dozen hydrogen atoms, there would be, 2 dozen hydrogen atoms would give me, in other words, I'd have 3 dozen total atoms. And so if I had 2 dozen hydrogen atoms, I'd have 3 dozen total atoms. Let's say if I had 20 H atoms, how many total atoms would I have? If I had 20 H atoms, I'd have a total of 30 total atoms. And so we could do things like this. There's another counting unit that's kind of like the dozen, except we call it the mole. So if I have 2 moles of hydrogen atoms, then I have 3 moles of total atoms here. This is 33.3%. And then it would be like 66.7% oxygen. By atom, or mole percent. Dozens, we don't really use that as a counting unit that much. Whereas when we look at this, how many total grams do we have? I rounded these, but if you add these up using all the digits in the calculator, then the percent hydrogen here is going to equal 11.209 grams of hydrogen out of a total number of grams of, we'll combine these two, we get 100 grams total, which gives us 11.209% hydrogen by mass. Okay, so these are what we call percentages, MV percentages, VV percentages. What are they? These would be percentages. Mass of the component over the total mass. So those are the formulas. Now, this is a number I get from chemical analysis, but there's another way to get this percentage. The other way of getting that percentage is by looking at something called molecular mass and formula mass. But before we do that, we got another example of this. Let's go with something like this. How would you name this? Oh, good. Yeah. This is called ammonium nitrate. So for ammonium nitrate, we're going to approach this at different levels. Is this, what is this? Is this mass ratio or atom ratio? That's a atom ratio. In fact, that's all we do. When we do formulas, it's always atom, or it could be dozen, For example, if I had 1 dozen N's here, then I'd have 4 dozen H's here, right? It could be 1 dozen N's, 4 dozen H's, 1 dozen N's, 3 dozen O's. Well, a dozen's a counting unit just like a mole, so, but a dozen's not that convenient. A mole is much more convenient. A mole is a lot more atoms. So if I had 1 mole of N here, how many moles of H would I have? H atoms? 4, and then 1, and then 3. And so when I look at this, this is an atom or mole ratio. Atom or mole of atom ratio. All right, so for ammonium nitrate, how many atoms of nitrogen are there? This is a little bit tricky because there's one in ammonium called, what was the charge on ammonium? Positive. And the charge on nitrate? Negative. And so there's 1 nitrogen in ammonium and 1 nitrogen in nitrate. And so the total number of nitrogen atoms in this is 2. So the number of nitrogen atoms equals 2. So we could do the same thing, a number of hydrogen atoms, 4. Number of oxygens, 3. So that's 7.1. Now, when we look at this, here, we could do the percent by atom, or moles of atoms. So I'm going to call it atom or mole percent. And the percent by atom would be, let's say here, I'm going to have 2 nitrogen atoms out of a total, how many total atoms are there? 9. 9 total atoms times 100%. And so the percent nitrogen in this is going to be how much? Two divided by 9 times 100. 22.2. 22.22%. Actually, I can keep going on here. This is percent by atom, or mole of atom. All right, that's fine. You know, that tells us 22% of the total atoms are nitrogen. But now let's do percent by mass nitrogen. How can I do the percent by mass nitrogen? Would I have to be given the numbers? Like, if you go back to this example, I gave you the numbers here. But is there a way to do this without being given the numbers? Here. It's a way I could figure it out. Yeah, I'm going to use the periodic table. And so this is it. And so in order to determine the percent by mass, I need to know how much of the mass is nitrogen. So I write the mass of nitrogen over the total mass times 100%. And so I can just kind of figure out these two things, you know, this one and this one. And then I can figure out the percent nitrogen by mass. Because what do you think is more useful if you're, let's say, if you're a gardener and you're gardening and you want to get some nitrogen in the soil. You want to figure out how much nitrogen is getting in the soil. Do you think it's more useful to have an atom percentage, or do you think it's more useful to have a mass percentage if you're gardening? A mass, for sure, a mass percentage. Whereas if you're just a chemist looking at this, you know, typically atom ratios or atom percentages are more useful in understanding chemistry, but if your goal is just to get a certain number of pounds of nitrogen in the soil, then you want to know the mass ratio or the mass percentages. And so what we're going to do is we're going to talk about masses now. How do we get masses? So we have different masses here. We have something called the molecular mass, or formula mass. For water, water forms molecules. And so when I form an individual water molecule, you know, are all the water molecules identical in the water sample? No, we're going to see a bunch. What do you think is the most abundant of the water molecules? Like, which water molecule is the most abundant? We might want to take a look at some data. What was that? You know, what was that book? Okay, probably not that book. We probably want to take a look at the other book. What was the other thing? CRC. CRC, which stands for the Chemical and Rubber Company. And the book's title was what? CRC. Does anybody recall the title of it? Probably if you just type in CRC, it'll pop up. Let's see. Cyclic redundancy check. CRC website. California Resources Corporation. Well, probably should start with the book, CRC book. Maybe I should type in CRC book. CRC exam secrets. Oh, this is it. The CRC Handbook of Modern Telecommunications. Is that it? Close. That was pretty close. There it is. We probably want to look at the CRC Handbook of Chemistry and Physics. CRC Handbook of Chemistry. Then let's look at this one, nuclear and particle physics. We want to come down to here, table of isotopes. Maybe they give us this is an online version. Well, anyway, what we'll do is we'll just use some other table, like this table here, and just took this off. But one thing you notice about this table is the mass is here. When you look at the mass, so this is for each one. When you look at the mass, what do you notice that's different between the entry and the CRC versus this one? The CRC had many more sig figs. Yeah, a lot of sig figs. Here, this is only going 4 decimal places, where the CRC went much farther, but it's okay. We're just going to do it in 4 decimal places here. But out of these 3 hydrogens, which one's the most abundant? In fact, this third hydrogen didn't even appear in our Brooks table. This third hydrogen is called tritium. The second hydrogen is deuterium. So this is hydrogen 1, hydrogen 2, and hydrogen 3. Hydrogen 3 is radioactive. It's negligible. But out of these 3, which one's the most abundant? The first one. And the first one weighs 1.0078. And so most of the hydrogen atoms in nature weigh 1.0078. Right? But what is this 1.0079? That's the average, you know. Are you going to find any hydrogen atoms that weigh 1.0079? No. You're going to find most of them weighing 1.0078, and some weighing 2.0141, 3.01. And so it looks like the most abundant water molecule should consist of the hydrogen 1. Which oxygen is most abundant? Oxygen 16. And then we want a hydrogen 1 here. Now the thing is, how much does this thing weigh? Well, we can figure out how much it weighs because we just add up the parts. And so we have 2 H1 atoms. 2 single atoms of a specific isotope sometimes are called nuclids. And so we have 2 H1 nuclids, hydrogen atoms of a specific isotope. And each of those weighs 1.0078, so it's going to be 2 times 1.0078 U, and that's going to give me 2.0156 U. And so that's 2 H1's worth of mass. And then I have my oxygen 16. The oxygen 16, I just have one of those that weighs in at 15.995 U. That's 1 at 15.995 U. Now, when we do addition, we look at how many decimal places we're allowed. So we're allowed 3 decimal places. So this is going to go 6. This is going to be subscripted because it's not significant. 5 and 5 is 10. It's 11, 10, 18. So I come up with 18.0106 U. So this has a mass of 18.0106 U. Now, what do we call this? We call this the molecular mass. The molecular mass is equal to the mass of an individual molecule. Individual molecule. That would be it. But when we're dealing with, samples of water, how many water molecules do you think there are in this? This is 18 milliliters, the 18.02 milliliters of water. How many water molecules? Well, yesterday actually, this was also mentioned in the epigenetics talk. Remember that YouTube epigenetics show? He was talking about how many cells are there in a human body?
Was this the stem cell that
Yeah, the stem cell guy. The stem cell guy who says, there's more to, how you turn out than just your genes, usually. So it depends on the medium. But he was talking about these cells, the number of cells in the human body. I might have cut that part out. I don't remember. If you watch the whole video, he talks about the number of cells in the human body, which numbers how many? You know how many cells there are in the human body? A lot. A lot of cells. Like a million cells? A billion? Trillion? Trillion? Getting close. What's after a trillion? Quadrillion cells? It turns out there's over a trillion cells in the human body. But I was thinking over a trillion cells, yes, that's a big number, right? That's a huge number of cells. And then he goes on to talk about how you lose about a billion cells a day or something like that. And then, billion's a big number, but to chemists, those are still small numbers. For a chemist, a trillion's like nothing. Because, in this is only 18 milliliters of water. How many water molecules are there here? A lot more than that. If I had 18 milliliters of water, like this, 18.02 milliliters of water, then there's going to be this many water molecules. What's that? 602, this is a million, right? How many is that? How many that is? Maybe. So if I go out to here, that's how many? That's only 3, 6, 9, 12 zeros is what? Trillion. And then 15 zeros would be quadrillion, right? And then 18 zeros would be the centrillion or something like that? Something like that? Pentatrillion? I don't know. But, what we do is this. We just do the numbers we know. So if you go here, thousands, 100,000, million, billion, trillion. We'll stop at a trillion. Oh, I got this wrong here. Here's a trillion. 12 zeros is a trillion. 9 zeros is a billion. So then this would be a million. And so in that small sample of water, there are 602 million trillion water molecules. Now, how much water do you have in your body? A lot more than 18 milliliters, right? And so if you're thinking about the numbers, the number is just huge, the number of molecules. And then you think about the number of atoms because, well, each water molecule has 3 atoms. There's a huge number of atoms and molecules. If there's a huge number, then sometimes what we want to do is we don't want to look at things at the particulate level like this. This is the particulate. If you're working with single molecules, then you got to know which molecule you're working on with, because if you were able to take like a molecular sized pair of tweezers and pluck one water molecule out of here, you know, it might be this. Chances are it's this water molecule, but it might not be. It could be a heavier one, right? And so if we're working with individual molecules, then we need to know what isotopes we're dealing with, because it's going to change the weight of this. But if we're working with like 602 million trillion water molecules, you know, it's too much to keep track of the individual water molecules at the particulate level. You know, as a percentage, we can't keep track of it, but particulate. And so what we do here is at the macroscopic level, we stop worrying about which isotope we're doing. And so at the macroscopic level, we just worry about the average water molecule. How much does the average water molecule weigh? And so, well, we have 2 hydrogen atoms. And so what's the average mass of a hydrogen atom? Yeah. The average mass of a hydrogen atom is this. It's 1.0079 U. It's the average. That's a weighted average. It tells me it's mostly H1. And so it would be 2 times. Okay, now, do we want to use all those digits? Actually, what we're going to do is we're going to limit it. We're going to limit it to 2 decimals. So I'll round this to 101 U, or we're going to round it to 3 decimals, 1008 U. Which one of these 2 we use depends on the other numbers. Ultimately, what we want is we want 4 sig figs in our molecular mass. 4 sig figs. This is more than 4 sig figs, so that's okay. But we want at least 4 sig figs. And so we're going to have 1 oxygen atom. What's the average mass of an oxygen atom? Yeah, 16.00. Okay, so I can use the first one. So I'll go 2.02 U plus 16.00 U, and that's going to give me my 4 sig figs. So I didn't have to. If I used the 108, then I'd have to round off 1 digit. So we're good. And so what this means is that the average water molecule weighs 18.02 U. This is the average molecular mass. The molecular mass being the mass of an individual water molecule. But in reality, is there going to be a water molecule in this sample that weighs 18.02 U? No, there isn't. There isn't. There's going to be one very close, 1801, but not 1802. But since we're working with so many, it's just more convenient to do this. It's the average. All right, so this is how I would have gotten my percentages. In fact, this is how I got my percentage because I calculated it for this. And so if I want the percent hydrogen by mass, then it's going to equal the mass of hydrogen. Well, unfortunately, I just erased it. But the mass of hydrogen is 2.02 U worth of hydrogen over the total mass. The total mass is the mass of the water, which is 18.02 U of H2O times 100%. And then when I do that, what does it come out to? So let's go ahead and do that. It's 2.02 divided by 18.02. That gives me 11.209 11.209% H by mass. And so we have different, we can come up with lots of different mass ratios that say the same thing. Lots of potential mass ratios. And so one of the mass ratios might be this, H 2.02, O 16.00. Right? So for every 2.02 U of hydrogen, I'm going to have 16.00 U of oxygen. Or, saying the same thing, it's going to be H 11.209, O 80. What was it? 88.790. Or, etc. All these have the same ratio. Same mass ratio. I could do the simplest whole number. If I do the simplest whole number, what do I have to multiply it by? If I do the simplest whole number, it's going to be a huge number. Do you see that? So we aren't really going to bother. Maybe like this. If I do like whole number, I might just go and multiply each of these by 1,000. So this would be 11,209, 88,790. That'd be a simple whole number, but you got to recognize that I rounded these. So. Now, let's do the same thing for ammonium nitrate. Let's calculate the percent by mass nitrogen, ammonium nitrate. But before we do that, let's take a look at this. What is this here? This is carbon dioxide. Are they doing the average mass or are they doing the individual molecule? The average. You can see the average mass of oxygen is 16.0. Since we use some of these elements over and over again, sometimes it's helpful to remember some of the masses to 2 decimal places. In fact, it is very helpful to memorize masses. And so a lot of people will just remember hydrogen. What's the average mass of hydrogen? 1.01 or 1.008. Now sometimes they leave off the units. Sometimes we leave off the units because of a relationship in chemistry. 1.01 U per atom. What's the average mass? Or 1.01 grams per mole of atoms. So let's say if I had 1.01 U per atom, let's say I had a dozen atoms. How much would a dozen atoms weigh? A dozen atoms would weigh, well, it would be 12 times that because a dozen's 12 atoms. 12 atoms. Okay, then I have a different counting unit called the mole, which we're going to talk about soon. So I'm jumping ahead, but if I had a mole of atoms, how much does that weigh? It turns out, well, it's going to weigh 1.01 grams. And so how many is a mole of atoms? Well, it turns out that a mole of atoms is this. A mole of atoms is 602 million trillion atoms. And is that if I had 602 million trillion hydrogen atoms, the total mass of that would be 1.01 grams. And so a mole is kind of a mole's a huge number. It's a huge number because a dozen's way too small for us. And then it's a bizarre number because why 602 million trillion? Why not some other number? And it's a bizarre number because if I had 602 million trillion atoms, then I would have 602 million trillion times 1.01 U. And when I take that number U, which is going to be a bizarre number, and convert it into grams, so I do a U to gram conversion, this is what I come up with. And so it's kind of like a magic number. The 602 million trillion is a magic number, you know, in that sense, that we can make predictions like this. And so this is how I figured it out here, you know, how many molecules of water I had, because I knew about how much this is. And so what we have is this. If we have 18.02 U average molecular mass, then this is for a single individual molecule. The other way we could think of this is if I had not just one molecule, but if I had a dozen molecules, it would be greater. But if I had much more than a dozen, a mole of molecules, then it's going to be a huge number. And if I take this huge number of U and convert it into grams, then this is what I end up with. I end up with 18.02 grams of water for every 602 million trillion water molecules. And so I know that because I have 18.02 U per molecule, that's going to mean the same thing as 18.02 grams per what we call mole of molecules, aka 602 million trillion water molecules. And then I know that 18.02 grams should have a volume of about 18.02 milliliters because water has a density of 1 gram per milliliter, 1.0 grams per milliliter. And so all I did here was I measured out about 18.02 milliliters, and then I could figure it out based on this relationship. And so we got to talk about this relationship in a little bit, but just introducing it now. All right, so let's go on to ammonium nitrate next. All right, if we look at ammonium nitrate, then what do you want? Do you want to do the, you know, how many different isotopes of nitrogen are there? Do you know? 2? Go back to the table and take a look. Yeah, just 2. Okay. We know that there are 2 isotopes for hydrogen, the third one being negligible, and 3 isotopes for oxygen. And so what we could do is we could do the same thing. We could get the mass of an individual, what do we call this, molecule? In other words, is ammonium nitrate a molecular compound? So here, you know, we could figure out the weight of an individual water molecule. So should we do the same thing? We could figure out the weight of an individual ammonium nitrate molecule. Is ammonium nitrate, now this is a tricky question, because when we have all nonmetals like this, it should be molecular. Versus, what's the alternatives? The alternatives are ionic, lattice, and covalent lattice. But it turns out we know where ammonium nitrate comes from. Ammonium nitrate comes from the ions ammonium and nitrate. And so even though it consists of all nonmetals, we call this an ionic compound. Do ionic compounds form molecules? No. And And so if I want the mass of this, and it's probably from here on out, we're not going to work with individual molecules. In fact, we don't even call it individual molecules. What do we call it if we're working with an individual unit like this? You know, what is one unit of ammonium and one unit of nitrate called? Like, for example, sodium chloride. Is there such thing as a molecule of sodium chloride? I just want to know how much a molecule of sodium chloride weighs. Do we have molecules of sodium chloride? No, instead we have what? What would I call them instead of molecules? It has a lattice. Do lattices have a distinct beginning and a distinct end? No, so what do we use for lattice type structures? These are all the vocab words. Do we use molecules? No. Instead, we call it a, do we call it a molecular formula? Let's go back even more. No, we don't call it a molecular formula. We call it a, starts with an E, empirical formula. And so what we can say is that this doesn't form molecules. Instead, it forms empirical units. The empirical units would be the simplest unit. And the simplest unit would be one ammonium, one nitrate. That would be an empirical unit. Or we could use the generic term. The generic term for empirical unit was what? Formula unit. And the formula unit holds for this too. I mean, we could call this a formula unit of water, but it's not as specific as the molecule of water. Well, over here, we probably should call this an empirical unit, but empirical unit and formula unit, there's no difference in detail there, so we'll just call it formula unit. And so what I want to know is how much does a formula unit weigh? How much does a formula unit weigh? And so here I could do the specific formula unit with a specific nitrogen isotope, hydrogen isotope, and oxygen isotope, but that's too much work. Instead, what we're going to do, especially since we're dealing with a lot of formula units, instead what we're going to do is the average. And so in this case, I have two nitrogen atoms. And what's the average mass of a nitrogen? Now, there are certain elements you see over and over again. These elements we want to remember, like hydrogen. Hydrogen is 101 or 108. The units are going to be, what are the unit choices I have? It's going to be U per atom or grams per mole of atoms. Or in other words, grams per 602 million trillion atoms. Okay, what other ones are common? Other ones that are common are carbon. Carbon's very common. And to 2 decimal places, what is carbon's average atomic mass? 12.011, but we're going to round it to 12.01. And then nitrogen, 14.01. Then oxygen, 16.00. And so these are the big ones here: hydrogen, carbon, nitrogen, and oxygen. Those ones we'd like to know or try to memorize. And so going back over here, and what I'm going to do is sometimes I'm going to leave off the units, because this number can mean 2 things because of the way the mole is magically defined. And so if I have 2 nitrogens, that's 2 times 1401, which is going to give me 2802. 2802 U for 2 atoms, or 2802 grams per mole. 2 moles of atoms. That's 2 nitrogens. How many hydrogens do I have? 4 hydrogen. Should I use the 108 or the 101? I'm going to use the 101 because it's still going to give me 4 sig figs at the end because of the addition subtraction rules. So this is going to give me 404. So I'm still about 2 decimal places here. And then I got 3 oxygens. 3 at 16.00 is going to give me 48.00. So this gives me 6, 0, 12, 0. 80.06. 80.06 for ammonium nitrate. And so the way I read this is like this. It's going to be 80.06 U per average formula unit, ammonium nitrate formula unit. Or it's going to be 80.06 grams per mole of ammonium nitrate formula units. And that magic works because of the way the mole is defined. So it gives us a lot of flexibility and it allows us to do lots of calculations in our head. Well, one of the calculations that I can do is calculate not the percent by atom of nitrogen. I can calculate the percent by mass nitrogen here. And so let's go ahead and do that. We're going to calculate the percent nitrogen by mass. That means I need to know the mass of nitrogen total and the mass of ammonium nitrate total times 100%. So what is the mass of nitrogen? The mass of nitrogen is going to be 2802 U or grams. So I have 2802 grams of nitrogen for every 80.06 grams of ammonium nitrate formula unit. So we'll just do grams. Grams of N for grams of ammonium nitrate formula units. Or I can do U. U of N for 80.06 U of ammonium nitrate formula units times 100%. So this is going to give me, let me finish with this and then we'll go on break. Do that. This is 2806 divided by 8006 times 100. 35.0. Now we got 4 sig figs were allowed, so in this division, so 35.04, and then I'll carry an extra one. So 8% nitrogen by mass. What was the percent nitrogen by atom? 22.22. So there's a lot. So for every 100 pounds of this fertilizer, we'd have 35 pounds of nitrogen we're adding to the soil, basically. All right, I'll stop here. We'll take a break and then